So last time we talked about the exergetic or second law efficiency for the turbine, symbol epsilon. Maybe you put a subscript T for turbine, maybe you leave it off. What is it? Think about two things. One is the turbine is to take energy out of the fluid stream and convert as much of that into shaft power. So W dot, what you desire, as much converted into shaft power as what comes out of the fluid stream, EF1 minus EF2. So that's the exergetic efficiency for a turbine. Same idea for a compressor or a pump. Now, this time, the goal is for this is going to be a negative. It's going to go into the fluid stream. So EF2 will be greater than the flow exergy coming in. Right? That's a compressor or a pump. More energy is going into the fluid stream. So, and this will be a negative quantity. So the exergetic efficiency is what we desire. We desire a large M dot EF2 minus EF1. And what does it cost? It costs W dot. Now you could put a negative on that so that the signs work out. Or you just talk about the power into the compressor or power into the pump. Make sense? All right. So we have a water pump. It intakes 6 kilograms per second of saturated liquid water at 10 kPa. So there's the pump. I'd like to ask a lot of questions. Is that absolute pressure or gauge pressure, 10 kPa? Absolute or gauge? How about I pause, I walk around, you answer, you write that down on your sheet of paper. You tell me. Let's continue. So this is the inlet right here at 1, and we said the pressure at 1 is 10 kPa, and outlet 2, inlet 1, outlet 2, and the pressure at 2 is 10,000 kPa. And the question is pressure at 1 10 kPa gauge or absolute? Here's another way of doing it. If I drill a hole or pop a hole in the pipe right there, does air rush in or steam rush out or water rush out? It's water that's in the pipe, right? It's under a pressure of 10 kPa. What's going to happen if I pop a hole in that water pipe, that the inlet to the pump, which is at 10 kPa? Air going to rush in or water going to rush out? Right? So air rushes in because it's 10 kPa is absolute pressure, and 10 kPa is less than atmospheric pressure, which is about 100 kPa. It's saturated liquid at 10 kPa. Describe the state 2 that comes out. Is it saturated liquid? Is it compressed liquid? Is it two-phase liquid vapor? Is it superheated vapor? What's going to come out of that pump? Superheated, okay. It's a pump. What's the purpose of that pump? Boost the pressure, right? Is it to boost the temperature or just boost the pressure? What's the purpose of the pump? Boost the pressure, and you really like to do it with minimal change in temperature because it does take energy to heat up water. You know, you can do it with the egg beater, but it's not good to have a pump act as an egg beater, just sort of whipping up the water, beating it up, churning it up. Viscous dissipation that can make it hot, not good. All right? So again, what is a state 2 coming out? Compressed liquid. Compressed liquid. Or somebody might say subcooled liquid because the pressure is much higher than the saturation pressure. But hey. Okay. Let's do this. Let's continue to look at it. The mass flow rate is 6 kilograms per second, and the isentropic efficiency of the pump, eta, is equal to 80%. Determine the power required to drive the pump. Okay, a couple things. When at a loss, make a long list of properties: pressure, temperature, specific volume, internal energy, enthalpy, entropy, all at state 1. And now these two pieces of information, that it's saturated liquid and the pressure at 1, fix the state, and I can go and I can get, let's say, the temperature at 1, which is Tsat at the 10 kPa, which is around 45.8 degrees C. I can get V1, V sub F, at the 10 kPa. That's going to be 0.00100102 meters cubed per kilogram. I can get U1. I don't need it, so I didn't write it down. I can get H1. That's H of F at 10 kPa, 191.83 kilojoules per kilogram. And I can get S1, which is S of F, 0.6493 kilojoules per kilogram Kelvin. Remember the state principle. Two independent pieces of information fix a state, what in this case, saturated liquid at 10 kPa, and I can get other properties. It's nice to have a common list of those properties. You can march over here to P state 2. What is T2? What is V2? What is U2? What is H2? What is S2? And that list can go on because we could have included EF1 and EF2, specific heats. There's a lot of other properties, but these are our dominant properties. So now they've given us P2. All right. How do I solve this problem? What fixes the state? Additional information fixes state 2. Is it T2 and P2? Is it V2 and P2? Is it U2? Is it H2? Is it S2? Is it EF2? What is other piece of information? And what we're going to do is because this pump has an isentropic efficiency, what we'll do is we'll consider state 2S isentropic, and then we'll consider state 2 actual, and we'll talk about P2, T2, so T2S, V2S, U2S, H2S, S2S, how like that, EF2S, and then you can have V2, U2, H2, S2, and EF2. This EF2 is just nauseating. Let's get rid of it. I think that's enough of the information there. You done?
That's all.
All right, thank you, John. So you understand about the state 2S and state 2? You isotropically compress it, and then you use the efficiency, 80% isentropic efficiency, to get the actual state 2, okay? So, what about state 2S? What other piece of information helps us fix the state? It's S, it's right. So let's get rid of these little tabs like that and make it clear. This one is known. What? S is known? Yeah, S is known. Guess what its value is? 0.6493. I'm running out of space, but units of kilojoules per kilogram Kelvin. So those two pieces of information fix state 2S, right? So then what we do is we say, I can go get 2S, T2S, V2S, U2S, H2S. How am I going to do that? It's kind of a weird way of doing it, but what I'm going to do is I'm going to try and tuck it in over here. 10 MPa T H S at 40 degrees and at 80 degrees. I know I'm running out of room. Here I'm going to put 80 degrees right there. Degrees C. I have H of kilojoules per kilogram and S of kilojoules per kilogram Kelvin. And from the table, for compressed liquid water at 10 MPa, that pressure block, we find that it's 176.38, just data out of the table, 0.5686, come down to 80, 342.83, and 1.0688. And you say to yourself, I have been given a value of 0.6493. I'm going to have to do some linear interpolation in the table to get this value of H2S. Do you see that? Does that make sense? Or did I go too fast? Thumbs up if it makes sense to you. Wiggle your hand sideways, up and down, or something if it says, I'm lost. Where are we at, huh? Are you okay with this? You're okay? Do you understand what I'm talking about? But a pressure block, what table number is that? A6 or A7? I can't remember the number of the table, but it's the last water table, the last one dealing with water. No, I'm sorry, there's another table after it, A6. It's table A5. Table A5 in our textbook, okay? So now you can also, for grins, find the temperature. Now I know that the purpose of it wasn't to heat up water, but it did heat up to 46.45. This is as good as your linear interpolation allows you to get, okay? This is the best we can do, linear interpolation in here. So what we find is this H2 right here is this H2S turns out to be 203.23. So the enthalpy of the flowing fluid went from 191 to 203. Why did it go up? Energy balance. The energy balance around this pump. What do we get from the energy balance? That the work or power in is equal to the mass flow rate times H2S, if this is S, minus H1, right? So the isentropic power, mass flow rate times H2S minus H1. Thumbs up? You agree? Likewise, you could say because of the efficiency, we find that the actual work is equal to the isentropic work divided by the 80% isentropic efficiency. Or you can also say that H2 is equal to H1 plus H2S minus H1 divided by the isentropic efficiency. So the actual enthalpy will be greater than the isentropic enthalpy. And when you crunch that number, we find that H2 actually comes in at 206.09. So that's the actual enthalpy. So the actual state is given by P2 and H2, the actual exit state of the water from the pump. All right? Somebody says, I wonder, could I come back to this table and put in the 206.09? And could I then look at the actual exit water temperature? Sure, it comes out at 47.14. So the water came in at 45.8. Isentropic compression, or in the pump, not compression, but isentropic pressure boost in the pump gives you the 46.45. That's an approximation due to linear interpolation. And then if you include the 80% isentropic pump efficiency, it's now 47 degrees. Got it? All right. All right. So the power required to drive the pump, that's going to be using this equation right here and that equation right there, that you find that the power required to drive the pump is equal to 80, I'm going to let you fill in the blanks, but here's the answer, 85.5 kilowatts. Just take those numbers that I've given you and use them. What's the part B? The rate of exergy destruction. How do I calculate the rate of exergy destruction? Well, it'll be the dead state temperature times the rate of entropy production. True? Is that true? Is that equal to the dead state temperature, the mass flow rate? From an exergy balance, you'll find S2 minus S1, the actual outgoing entropy minus the incoming entropy in the water. So you just do the other interpolation this way to get S2. And so S2 in that table comes in at 0.65788. So use that value for S2. S1 was given right over here. And you calculate the rate of exergy destruction is 15.3 kilowatts. Does that make sense? Did you see how we did it? I wanted to put this table up right here because you use that table twice. You use it to interpolate to find state 2s, and then in state 2 actual. All right? Okay. The last one, what's the exergetic efficiency? Well, the exergetic efficiency is what we desire. We want that power that's supplied. We're supplying 85.5 kilowatts of power. We want that to go into boosting the flow exergy of the water. True? So we want it, the mass flow rate times EF2 minus EF1 divided by W dot. Or a short way of writing it is what goes into the fluid stream, increasing the exergy flow of the water through the pump, divided by what came in the device by the shaft, the power that was supplied. You could rewrite an exergy balance equation. What came in with the shaft power into the pump went two places. It either went into increasing the flow rate of the fluid stream, or where did it go? It was destroyed through irreversibilities. So you can take that numerator and replace it by what went in minus the destruction divided by what went in. So we already know that what went in was 85.5 kilowatts minus the destruction 15.3 kilowatts, 85.5 kilowatts. So we find the exergetic efficiency to be 82.1%. I know it's a subtle point, but there's a difference in the numeric value between the isentropic efficiency and the exergetic efficiency. They're close for pumps and compressors and stuff, but they're not spot on. They're not the same. 80% is close to 82%, but it's not the same number. Okay? It's slightly different definition of the efficiency. Ready to press forward? Do you have any comments on that? You see how we did it? They do have things called computers, and they do have software. And yes, you can input these, and you don't need to do the linear interpolation, and you would get slightly different answers in software. But using the tables in our textbook, you can get an answer for this problem, and it's good enough. All right? And no software is allowed on exams. So there you go. Let's talk about a second law efficiency for a heat exchanger without mixing. So we have a hot stream, it just flows through from 1 to 2. And we have a cold stream from 3 to 4. And the heat transfer is from the hot stream to the cold stream, but it's not to the surroundings, it's just between the two fluid streams. And so thinking about exergy and the exergy associated with the fluid flowing, what you have is the outlet flow exergy of the hot fluid is going to be less than the inlet flow exergy of the hot fluid, right? Some energy went out of it. Its capacity to do work is lower. How about for the cold fluid? This is now greater than the incoming cold fluid flow exergy. So you think, okay, we'd like to do it as efficiently as possible. Here's a definition of efficiency. The exergetic efficiency is that what came out of the hot goes into the cold. How much comes out of the hot? Well, we'd like all of the exergy that came out of the hot to go into the cold, but it's not going to all come out of the hot and go into the cold. Some will be destroyed. So this is what goes into the cold, the mass flow rate of the cold, times EF4 minus EF3. True? What came out of the hot? The mass flow rate of the hot times EF1 minus EF2. So there's a good definition of exergetic efficiency for a heat exchanger that has 2 inlets and 2 outlets. It's without being mixed. How about if I have a heat exchanger where it's mixing, the 2 fluids are mixed. The hot fluid comes in, it goes out. The cold fluid goes in, it goes out. It's as if state 3 is a combination of the cold and the hot. It's at the lukewarm. How do you like that for a description of state 3? So you still think about exergy flowing from the hot to the cold. And so you want as much to go into the cold, what comes out of the hot. So the exergetic efficiency would be the mass flow rate of the cold times EF3 minus EF2. That's how much is added into the cold stream. It comes out of M.1, the hot stream, EF1 minus EF3. Notice EF3 is here and there. It's the same EF3. Well, F3 is, here, put them in order. EF1 is going to be greater than EF3, which is greater than EF2. This is sort of the hot. This is the cold. And guess what the middle one is? The warm. Make sense? Yep. How about the exergetic efficiency of a heat engine? In general, a heat engine, that's a concept we were introduced in Thermal 1, is a device typically running in a cycle which intakes Q sub H, heat transfer from a high temperature reservoir. What is the temperature of that high temperature reservoir? TH. So the heat comes into the heat engine at or across a boundary at temperature TH, right? How much heat comes in? QH comes in. We try to convert as much of that energy transfer into work, but we know that all heat engines have to reject some Q sub C to a low temperature thermal reservoir, right? And so the heat transfers like that. So from the first law, we know that QH is equal to W plus QC. What came in had to go out. It either went out as work or went out as heat transfer to the cold sink. We also recall the thermal efficiency. What we were introduced to in the previous class is the thermal efficiency for the heat engine. It's what we desire. We'd like a lot of work out over what it costs us to run. That QH supplied is what costs us. Now you may still do something useful with QC, but typically at this point we say QC just heats up the environment. It just makes our atmosphere warmer, right? It just heated up a lake, heated up the river, heated up air around us, but it didn't do anything useful. The only thing useful was that workout. Then also we recall for the Carnot. Carnot, what do you mean by Carnot? It's the maximum, the best heat engine you could ever design. You had the Carnot heat engine, the Carnot thermal efficiency, and it boiled down to 1 minus the temperature of the cold divided by the temperature of the hot. So if you knew the high temperature reservoir that supplied the heat, the low temperature sink, TC, you could calculate right away the maximum thermal efficiency. Maybe that thermal efficiency is 40% or 30%, right? But now we're going to talk about an exergetic efficiency. What is the flow rate of exergy coming in, or how about just the amount of exergy coming in with QH that comes in? Do you remember the equation? It's proportional to QH. What was that constant in front of it? 1 minus the dead state divided by the temperature that it comes in. What is the flow of exergy with the work going out of the heat engine? It's proportional to W, What is the purport constant right in front of that? 1. It's a 1-to-1. It's in the energy form that we want. Work is in the energy form that we want, right? Okay, what is the exergy that goes out with the heat at the cold? 1 minus T naught over Tc QC. Okay, so those are the exergy flows. True? All right. We have exergy balance. Wasn't this an energy balance equation right here? QH is equal to W plus QC. Exergy balance. Well, first of all, let me back up. You could think about if Tc is greater than T naught, how you still have the potential to do something useful with QC. True? But most times Tc isn't greater than T naught. Most times Tc is T naught. You're dumping heat to the local ambient environment. Right? So in the analysis, add that. We can always go back and revisit it. But if you do that, what is the flow of exergy with QC? If Tc is equal to T naught, if the cold temperature sink is equal to the dead state temperature, is 0. See that? So let's use that now with our exergy balance. If we do our exergy balance, we have what comes in, E with QH, is equal to E that goes out with the work. We had E that goes out with the QC, which is 0. And then what do we have else? Do we have anything else in our exergy balance? Any that is destroyed. Yeah, and anything that's destroyed. Okay? All right. So now you have exergetic efficiency. What would be a good definition of exergetic efficiency? It's what I want. What do I really want? I want the flow with the work over what it costs to drive it. That's the flow with the heat supplied. Or it's W over 1 minus T naught over TH times QH, or W over QH divided by 1 minus TC over TH. So the exergetic efficiency is a ratio of the actual thermal efficiency divided by the Carnot thermal efficiency, is it not? Can you see that? So what we did was renormalized. Instead of saying the best you can do is 40% because TH and TC limit you to that, you say the best you could do is always 100%. That's what you've done. You've renormalized everything. So the efficiency is on a 100% scale, which makes a lot of sense to people, engineers and everybody else. I'll tell you, you don't have to listen to the news long before you hear somebody out crabbing about the poor technology and the poor engineering into power plants and how they just waste energy. You know, the typical coal-fired power plant can only, convert 40% of that energy. 60% of that energy squandered by silly mechanical engineers who can't do a good job. How do you like that? You say, time out, buddy. We're redefining efficiency. When you redefine efficiency, you're back to where you're looking good, right? But it makes sense. There's no coach tells kids, okay, kids, we got an important football game. Go out there and give it your 40%. That's the maximum you can do today. It's this day of the week, this whatever. You're only 12 years old or 15 years old. Go give it your 40%. No, he's going to tell them go give it 100%, right? Anyway, let's do this. Let's solve some problems. Calculate the exergetic efficiency of a heat engine where TH is 600 Kelvin, TC is equal to the dead state, which is 300 Kelvin, and QH is equal to 1,000 kilojoules, and it flows into the heat engine, and the work coming out the heat engine is 400 kilojoules, meaning what is QC? Can you figure that out right away? 600 kilojoules, that's right. So you could put the little thermal reservoir there. So what is the exergetic efficiency, or the second law efficiency? Well, why don't you do this? Tell me what the actual thermal efficiency of this plant is. It's what we want over what we had to pay for. 400 over 1,000. What is that? 40%. What is the Carnot thermal efficiency? 1 minus TC over TH. 1 minus 300 over 600. That's 50%. So don't report the thermal efficiency of the power plant. Report the exergetic efficiency of the power plant, which is 40% divided by 50%. It's 80%. Hey, that looks a lot better, doesn't it? True? How many people recall when you first time you saw that thermal efficiency, thermal 1, you're like, the best you can do is 40%? That doesn't appeal to me. Maybe you were bothered by that. Well, here you go. Now you can get it straight, okay? Talk about exergy, the ability to do useful work. That's what exergy is all about. Ready to solve another problem? So we have a flash chamber. It's used to generate streams of saturated vapor and saturated liquid. So you come in at state 1, and you have 2 outlet states, state 2 and state 3. Okay? So you bring in some fluid, and you bring out a pure stream of saturated vapor and a pure stream of saturated liquid. It's a flash chamber. Basically, there's a restriction right here, the pressure drop. You use the presence of gravity to collect the liquid on the bottom and the vapor on the top, and you extract the vapor off the top and the liquid off the bottom. It's saturated inside, okay? That's what, this is not a complicated device. It's a flash chamber. Why do they call it flash? Because some of it flashes the vapor, but most of it still remains. If it comes in at liquid, it still is liquid when it goes out. So most of this 30 kilograms per second is still going to go out. So mass flow rate of 3 is going to be, can't be greater than 30 kilograms per second, but it could be like 25, 27 kilograms per second, leaving, much smaller amount going out as a vapor. Flash meaning some of it went into the vapor. Okay, the chamber is well insulated, so there's no stray heat transfer with the surroundings. For the data given in this table, state 1, state 2, saturated vapor, state 3, saturated liquid. The mass flow rate coming through at state 1, we don't know here and here for 2 and 3. Kilopascal, 700 kilopascal, and they both go out at 220. So P2 and P3 are the same, 220 kilopascal. It comes in at 160. Okay. There's some enthalpies and entropies, enthalpy, entropy, and enthalpy, entropy. They're given to you. So they use the data in the tables, save some time so you don't look up data in the appendices, which can be very time consuming, right? So first question, what's the saturated liquid mass flow rate? I want a symbol for that, and I want to know the units. What's symbol, and what are the units? Similarly for B, and then also for C. So I'm going to pause. I want you to give me the symbol and the units for the answer for A, B, and C for this problem. All right, so what we're looking for is the mass flow rate of the saturated liquid. That's mass flow rate 3. What units? Kilogram per second. True? Mass flow rate through state 2, the saturated vapor, kilogram per second. True? Now the rate of exergy destruction, E dot D, in units of kilowatt. Kilojoule per second or kilowatt. All right? All right. So now, how do I solve for, I have 3 questions. How do I start the process? Okay, give me a suggestion. Pardon? Yeah, they're all going to be balances. All right, what are the three? Mass, energy, and exergy or entropy, and then exergy. We have 4 balance equations we can put for each. For this open system, which is a control volume, 1 in, 2 outs. And so what does the mass balance equation look like? M dot 1 is equal to M dot 2 plus M dot 3. Is this the symbol I use for one of my unknowns that I want to calculate? Is this a symbol of one of the unknowns that I want to calculate? So there you go. I have one equation with 2 unknowns. Good luck. You can't solve it. You have to have another equation. Which equation do you want to do? Energy balance. How about enthalpy 1 times M dot 1 is equal to enthalpy 2 M dot 2 plus enthalpy 3 M dot 3. You say, doesn't that look like a couple steps you skipped, Professor? Yes, I did. I skipped a bunch of steps. You shouldn't until you get really, really familiar with solving a lot of problems. Then with confidence you can say, I know the algebra here. I've done it so many times, right? What about the entropy balance? S1 M dot 1 plus sigma dot equal to S2 M dot 2 plus S3 M dot 3. How many people like that? The sigma dot's a gain, so I put it over there with the 1 coming in, like an in, okay, into the control volume. How about for exergy? EF1 M dot 1 equal to EF2 M dot 2 plus EF3 M dot 3 plus, what is our symbol for exergy destruction? E dot D. Why did I put the destruction over there on the outs? Because it's like a removing. It's removing ability to do your work. Now, I would take the first 2 of these equations and combine them because I know all the H's and I just have 2 unknowns, M dot 2 and M dot 3, in 2 equations. I think the algebra you can work through. True? All right, you could solve that. Then the next one would be, what is the rate of exergy destruction? You can use this equation, or you can just use the entropy equation where the rate of exergy destruction is the rate of entropy production times T naught. So either, a lot of students like to solve for entropy balance, get the rate of entropy production, multiply that by T naught, you got the rate of exergy destruction. True? Otherwise, you can come out here and create another column, the flow exergy, and calculate those values, and then do it with an exergy balance. I ran out of time. Thank you for your attention. Have a safe weekend. I'm sorry? Oh, I would do this. Well, yeah, yes. I wouldn't say a lot easier, just easier.